well, what everything's made of.
Yeah, we're exploring the forces that bind the most fundamental bits of matter together.
Exactly. We've got some really interesting analysis lined up, looking at forces we know about, and some pretty out there ideas about forces we haven't found yet.
And the goal, as always, is to pull out the really crucial stuff for you, without making you feel like you're back in a physics lecture.
We want those aha moments, not the ha moments. So 2 main things today.
That's right. First, we'll unpack the force-binding gluons, that's the bedrock stuff, quantum chromodynamics, QCD, solid science.
Okay.
Then we'll venture into more speculative territory, this idea of a metaforce, maybe binding things inside an electron, if such things even exist.
Right, so what we know for sure versus what we're theorizing about. Sounds good. Let's dive in.
Okay.
Let's start with QCD, quantum chromodynamics. This is the strong nuclear force, right? The big one.
It is. It's what holds quarks together inside protons and neutrons. I mean, fundamentally, it holds the nucleus of every atom together. And crucially, it also describes how the force carriers themselves, the gluons, interact.
Now, the analysis talks about color charge. This isn't like red paint, obviously.
No, not quite. It's a different kind of charge, distinct from electric charge. There's red, green, and blue, and also anti-red, anti-green, anti-blue.
Okay.
Think of it as a more complex property. Electromagnetism has one type of charge, positive, negative. The strong force needs 3 types, described by this mathematical group called SU3.
Right, more complex rules, and the particles carrying this force are the gluons.
Exactly. Gluons mediate the strong force, but here's the kicker, and it's a huge difference from electromagnetism.
Which is?
Well, photons carry the electromagnetic force, but they don't have electric charge themselves. Gluons, however, do carry color charge.
Ah, okay, so they're participating in the force they're carrying.
Precisely. And there aren't just 1 or 2 types. There are 8 different kinds of gluons, each carrying combinations of color and anti-color charge.
8 kinds.
Oh.
Wow. And this self-interaction, gluons interacting with other gluons, that's key.
It's absolutely fundamental to QCD. It leads to some really, really weird effects that you just don't see with other forces, like confinement.
Confinement. Okay, sounds like things being trapped.
That's pretty much it. Unlike gravity or electromagnetism, which get weaker the further you go, the strong force between color charges doesn't. It stays constant, or maybe even gets stronger as you try to pull quarks or gluons apart.
So you can't just yank a quark out of a proton.
You can't.
Yeah.
The energy required would be enormous, enough to actually create new quarks and antiquarks from the vacuum, which would immediately pair up with the ones you're trying to separate, forming new particles.
Huh. So you never see a lone quark or gluon floating around?
Never observed, nope. They're always confined inside composite particles that are overall color neutral. Like baryons, protons, neutrons made of 3 quarks, 1 red, 1 green, 1 blue, or mesons made of a quark and an antiquark, like red and anti-red.
Nature insists on color neutrality for anything we can see directly.
That seems to be the rule. It's why we only see integer electric charges in bulk matter. Even though quarks have fractional charges, they're always bundled up.
Okay, but then there's this other concept mentioned, asymptotic freedom. Sounds like the exact opposite.
It does, doesn't it? But it applies in a different regime at very, very short distances, which means very high energies.
So like deep inside the proton.
Exactly. When quarks and gluons get extremely close together, the strong force between them actually gets weaker. They behave almost like free particles.
So it's like they're in a crowded room up close, they can move around easily, but try to pull one out the door and everyone grabs onto them.
That's not a bad analogy, actually. The interactions are weak at short distances, but incredibly strong at larger distances.
And these gluon-cell interactions, they're not just about confinement, they're also key to the dynamics inside the proton or neutron.
And maybe even making glue balls. Particles of pure glue.
That's the prediction. Glue balls are theoretically possible bound states made just of gluons, no quarks. Very hard to find experimentally, but QCD predicts they should exist.
Wild. Okay, but here's something in the analysis that really jumped out at me. Mass. Where does the mass of a proton come from?
Ah, yes. This is one of the most profound consequences of QCD. If you add up the masses of the 3 quarks inside a proton, you only get a tiny fraction, maybe 1%, of the proton's actual mass.
Only 1%. So where's the rest coming from?
It's coming from the energy of the churning, interacting gluon field inside the proton, and also the kinetic energy of the quarks whizzing around. Remember EMC squared?
Energy equals mass times the speed of light squared. Yeah.
Well, that intense energy locked up in the strong force field is the mass. Most of the mass of the visible matter in the universe isn't from the fundamental particles themselves, but from the energy binding them together. Wow, okay. That definitely qualifies as an aha moment. The stuff is mostly energy fields.
Pretty much. The energy of interaction.
All right, so that's QCD, established, complex, explains a lot, including where mass comes from. Now let's shift gears completely. Sub-electron particles.
Right. Entering the realm of beyond standard model physics.
Because the standard model, our current best theory, says the electron is fundamental, point-like, no smaller bits inside.
Correct. As far as any experiment has ever shown, the electron has no size, no internal structure. It behaves like a true point particle.
But physicists are always asking, what if?
Right.
Right. So what if the electron is made of smaller things, preons, rishons, whatever you call them?
Exactly. It's a theoretical possibility people have explored for decades. Often driven by wanting to explain patterns the standard model doesn't. Like, why are there 3 generations of particles? Why do they have the masses they do? Maybe there's a simpler underlying structure.
And if these hypothetical preons exist inside the electron, they must be held together by something.
Precisely. And that something would have to be a new, undiscovered fundamental force. The analysis we looked at calls it the metaforce, just as a placeholder name.
A placeholder for a force we have absolutely no evidence for.
Zero direct evidence. It's purely hypothetical. But it's interesting to think about what properties such a force would need to have if it existed.
And the analysis suggests drawing analogies with QCD, even though it's happening at a completely different scale.
Well, yes and no. You wouldn't expect this metaforce to be directly derived from QCD. The energy scales would likely be vastly higher, think TeV scale, or way beyond, compared to the Medvedev scale of QCD, and the charges involved would be totally different.
So not color charge, some new kind of metacharge.
Exactly. But the framework used to describe QCD, that's gauge theory, has been incredibly successful. It describes electromagnetism, the weak force, the strong force. So it's natural to assume any new fundamental force, like a metaforce, would also be a gauge theory.
Meaning it would have its own specific rules, its own symmetry group, like SU3 for QCD, but maybe SUN or SON, or something else for the metaforce.
Correct. It would have its own specific mathematical structure, its own set of metacharges, and its own force carriers. You could call them metagluons by analogy.
And these metagluons, like QCD gluons, might interact with each other.
That would be a key feature if you want confinement. If electrons are composite, those internal parts must be incredibly tightly bound. We've probed electrons down to tiny distances, like 10 to the minus 18 meters, and seen nothing.
So whatever holds them together must be immensely strong and likely exhibit confinement, just like QCD prevents free quarks.
That seems almost certain, yes. The metaforce would need its own version of confinement, operating at a much, much higher energy scale, to keep those hypothetical preons hidden inside the electron. These metagluons would likely self-interact, creating a force that doesn't weaken with distance.
And maybe asymptotic freedom, too, at incredibly tiny scales within the electron.
It's plausible, yes. The metaforce might weaken at extremely short distances, allowing the preons to move quasi-freely within their tiny prison.
The analysis also touched on this idea that maybe the different generations of particles like the electron, the heavier muon, the even heavier tau could just be different arrangements or excited states of the same underlying preons.
That's one of the big hopes for preon models. Could they provide a simpler explanation for the 3 families of quarks and leptons? Maybe the metaforce dynamics are responsible for generating these different states and their very different masses.
That would be elegant, a simpler set of building blocks.
Extremely elegant, if it worked. It could potentially unify a lot of the parameters in the standard model that currently just seem arbitrary.
But elegance isn't enough. There are big problems, right? The analysis highlights some major differences and challenges.
Huge challenges. First, as we said, the metacharges and metagluons are distinct from QCD. The energy scales are totally different. And critically, whatever this metaforce does, it cannot mess up the incredibly precise predictions of quantum electrodynamics, QED for the electron.
Right, like the electron's magnetic moment, that tiny wobble it has in magnetic field. QED predicts it with amazing accuracy, and experiments confirm it. Any substructure can't spoil that agreement.
Exactly. That agreement is one of the triumphs of modern physics. Any preon model has to be constructed very carefully to preserve results like that.
And then there are deeper theoretical problems, like the mass problem.
Yes, this is a killer for many models. If the metaforce is super strong, Operating at, say, the TeV scale or higher, you'd expect the bound states like the electron to also have masses around that scale, but the electron is incredibly light, only half in MeV.
So why is it so light compared to the energy scale holding it together?
Good question. It's like building something tiny and light out of massive bricks held by superglue. It feels wrong. There are theoretical ideas like something called Hooft anomaly matching conditions that try to constrain how this might work, ensuring certain properties match between the preon level and the composite level, but it's very difficult to build a model that naturally produces such light particles.
You need some mechanism to protect the electron's lightness from that huge binding energy scale.
You do. If the preons themselves have mass, why is the electron so much lighter than other potential combinations? If the preons are massless, why don't we see a whole bunch of other light composite particles made from them? It's tricky.
And the ultimate hurdle. Any successful model has to reproduce everything we see in the standard model. All the quarks, all the leptons, their charges, how they interact via the known forces.
It's a monumental task. You're not just explaining the electron, you have to explain the whole particle zoo and all its interactions based on these hypothetical preons and the metaphors. Very, very tough.
And just to reiterate one last time, zero experimental evidence so far.
Absolutely none. Electrons still look perfectly point-like.
Okay, so let's try and wrap this up. We've looked at two forces, or potential forces. One, the strong force binding quarks and gluons via QCD is real, well-tested, and explains fundamental things like nuclear structure and even mass itself.
A cornerstone of our understanding, yes. And the other, this hypothetical metaforce binding sub-electron particles, is, well, it's fascinating speculation, an attempt to look deeper, motivated by patterns in the standard model.
But it remains purely theoretical, facing huge challenges, both conceptually and in terms of matching reality, plus a complete lack of experimental hints for now.
Correct. What's interesting, though, is seeing how the principles we learn from successful theories like QCD gauge theory, confinement, asymptotic freedom might potentially apply, maybe in very different ways at entirely different energy scales. It shows the power of these theoretical frameworks.
It does. It suggests that even if the details are different, the underlying language of physics might have recurring themes.
But it's so important for you listening to distinguish between the established science of QCD and the purely speculative nature of preon models and metaforces.
Absolutely. For now, the electron is fundamental. But it does leave you with a thought, doesn't it?
It does. Could these mathematical tools, these gauge theories that work so well for the forces we know, actually be hinting at new layers of reality, even if we can't see them directly yet?
What would it mean if the things we think are the ultimate building blocks actually aren't? It kind of changes everything.
It really makes you wonder what else might be out there, built on potentially even deeper principles. Something to ponder.